Hello and welcome back. So today we're going to be getting into closed pipe resonance as well as the Doppler effect and shock waves and things like that. So this is just a picture of the fourth harmonic of a closed pipe. So this is the closed end of the pipe, and then this is the object that's making the sound, which they're considering, I guess, to be open. But and again, you can see this has four antinodes. One, two, three, four. Let's try that again. Four. Oh, this has 4.5. This is, well, 4.25. This is still the fourth harmonic, I'm pretty sure. Again, you can see you've got a pressure antinode located here by the closed pipe, and would it be the fifth? We'll cover that when we get to it. That'd be the first one. I think it's the fifth actually. One, two. Sorry about the brain fart. Yeah, this would be the fifth harmonic, and we'll get into why that is in just a second. So we can see we've got a pressure antinode at the closed end. Then here we have a pressure node at this end. So the density of the atoms is staying pretty consistent here, whereas the density of the atoms, they get squished and then unsquished and that sort of thing. So that's what it looks like. So for a pipe that's closed at one end, okay, because the ends of the pipe that are different, you want the ends of the wave to be different as well. Instead of starting and ending with a node, okay, you're going to start with a node and end with an antinode. Okay, so you're going to start with a node and end with an antinode, and that's because the pipe ends are different. So what fraction of the wave is this section right here? Okay, this right here. So, well, this is half right here. This is 1 right here, and this is half of that half. So that's 1/4. So it's 1/4 of a wave. So the first harmonic in a closed pipe is 1/4 of the wave. Now, to get to my next one, we need to start at a node and end at an antinode. Okay, so we're going to end here. So this is going to be your next standing wave. So so that's right here. Now, what fraction of the wave is this? This is 3/4. Okay, and then the next one is going to be where we end in an antinode over here. Okay, and so that's the third harmonic, which is 5/4 of lambda, and then you can kind of see what the pattern would be here. 1 plus 2/4 lambda, or n lambda over 2 minus 1/4. I think that's what I said. So this is the equation that relates the relationship between the length of the pipe and the harmonic number for a closed pipe wave. Okay, so pipe is 0.56 meters long. What would be the frequency of the first two harmonics if the pipe is open on both ends and if it's closed at one end? Okay, so first two harmonics for both. So let's look at the simplest example. So here we're open. We know how to do this. We start and end with a node. So that means that this is lambda over 2. Okay. And so lambda itself is going to be twice that because only half a lambda fits in between that. So that's 1.12. Okay. The speed of sound we said was 331 meters per second. Okay. So V equals lambda F. Plugging in, we get the first frequency is 296 hertz. Okay. The next frequency we're going to get is with n equals 2. So here we've got a full wavelength that fits between the ends of the pipe, and that tells us that lambda is the length, which is 0.56. So 331 equals 0.56 times the second frequency gives us 591 hertz. Okay, the next one that we're looking at is closed. Okay, so the fundamental harmonic for the closed the fundamental wavelength and frequency of the first closed harmonics. That didn't come out quite right, but it'll work. So here, this is 1/4 of lambda. Okay, so because it's only 1/4 of the wave, so we're going to multiply 0.56 times 4, okay, and we're going to get that the wavelength is 2.24 meters. Okay, plugging that into V equals lambda f, we get that the first frequency of the closed harmonic is 148 hertz. Notice that just by closing off, so if here the ends of the pipe are open, I'm going to get a frequency of 296 hertz. Okay, if I put my hand over one end of that pipe, that frequency is going to drop down to 148 hertz. And I can probably demonstrate that for you if you remind me. Okay, so the next one we've got where this is equal to 3/4 of lambda fits in the pipe, which means that lambda, the second harmonic lambda, is equal to 0.747 meters. Okay, so 4/3 times 0.56. Plugging into V equals lambda f, the second frequency of our closed harmonic is 443 hertz. Okay. What is the shortest open and closed pipe that will resonate a 12,000 hertz pitch? Again, assume the speed of sound is 331 hertz. Okay, so we'll start with an open pipe, the pipe that's open on both ends. And so if it's open on both ends, my first harmonic is going to be where half of a wave fits between the pipe. Okay, half of a wave fits between the pipe, which means my total so what we need to do is figure out the frequency, or I'm sorry, the wavelength of this, figure out lambda, and then this will be half that. Okay, so 331 equals lambda times 12,000, V equals lambda f. Okay, we get that the wavelength is equal to 2.76 centimeters, or 0.02758 meters. Okay, so half of the wave here is going to fit between there, which means the wave is twice the length of the pipe. So we get twice that the wavelength gives me 0.0138. Okay. And here we've got, so that's the length of the pipe. And if we go to a closed pipe, it'll resonate with only 1/4 of that wavelength. So this is my wavelength, so divide that by 4, and that gives me the wavelength of that. So this one is 1.3 centimeters. This is 0.69 centimeters. Definitely a shorter pipe will resonate the same pitch if it's closed. Okay. Okay. I'll leave a note for myself. I just thought these were cool animations and decided to include them. Okay. All right. On to the Doppler effect and some related phenomenon. Okay, if I were to drop a piece of wood into a lake, it would bob up and down, sending waves radiating out. Okay, so those waves are radiating out. Now that's what they look like if the wood is stationary, meaning it's not traveling to left, right, or up or down. Okay, you see something different where it is moving one to one side or the other. Okay. So if the rock is moved as it's bobbing, so if you're pulling it with a string or something like that, you're going to see that those waves get bunched up on the side that the log is moving towards, okay, and they get spread out on the side that the log is moving away from. Okay, and this really is the Doppler effect. Okay, notice those waves are sent from where the rock is, or the log is, and as it's moving, the waves are constantly being sent from different locations. Okay, and that's why they're not concentric in the Doppler effect. If it's stationary, the circles are concentric, but if it's moving, the circles are not concentric, and they get bunched up on the side that it's moving towards. Okay. All right. So if I were to look at the frequency of the waves that are observed by a person at location A and a person at location B, okay, let's see how their frequencies would compare. So for person B, the frequency is boom, 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 boom. Okay. For person A, the frequency is boom, 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 boom. Okay, so person B perceives a much higher frequency, much higher than person A. So basically, if the source of the wave is moving towards you, you perceive a higher frequency than the wave is actually emitting. Okay, than the source is actually emitting. If the substance is moving away from you, if the object is moving away from you, then you perceive a lower frequency of the wave. All right. So I just wanted to show you the Doppler effect with where'd it go? Just had this. Maybe I'll need to pause this again. There it is. Okay. So here's the Doppler effect. The source of the sound is right here, and it's moving directly down. And you can see that the wave fronts get bunched up on the side that it's moving towards, and they get spread out on the side that the source is moving away from. Okay. And let's take a look at that in 3D. So here the source is moving up and to the left like so. You see that the waves are a little more spread out here, and they're a little more bunched together here. So over here we would perceive a higher frequency, and over here we would perceive a lower frequency of that wave. By higher and lower, I mean compared to what the frequency that the object is actually emitting. Okay? Okay. And if a sound source like an ambulance was moving towards you and then past you, what would the perceived sound be? Well, as it's moving towards you, you're going to perceive a higher frequency sound. Okay, when it's right in front of you, okay, you're going to perceive the actual frequency of the sound of the siren. Okay, and then as it starts to move away from you, that's going to get shifted to lower frequencies. So that's kind of why you hear that sound, that kind of when cars pass you, like speed fast cars. You're getting that shift from high to low, and that's what you get. Okay, so now if the source moves, the frequency is shifted. What if the observer moves and the ambulance or whatever is stationary? You still perceive a higher pitch sound. So an ambulance is stationary, and then you suddenly start running back towards it with all your speed. Would you still notice a Doppler effect or not so? Well, the answer is you would, okay, because you would be running into those wave fronts, increasing the frequency at which you were running into them. And then as you pass the ambulance and started running away, you'd be kind of running with the wave fronts. So you're going to perceive a lower frequency. The waves are going to pass you at a lower frequency. Okay, so what about if you perceive a wave from reflecting off of a moving object? Okay, so would the Doppler effect work then? So here I've got a wall, and the wall is going to start moving. This is my wave creator, so it's going to just shoot balls, and the balls represent wave fronts. Okay, so we'll get it going. We'll see. Okay, so this is what it looks like if the wall is stationary, okay, where these are received with the same frequency as what they were emitted. So you can see they're being perceived at the same rate. Okay, let's get the wall moving. Okay, now let's see if we notice a difference. Okay, now I couldn't get the balls to bounce off just because it made the animation complicated. But compare the rate at which the balls are being hit. They're going to reflect at the same rate that they're being bounced. It's not going to accumulate any waves or balls. It's going to bounce them off as soon as they hit. So compare the frequency at which they strike the wall compared to the frequency at which it's hit. Let's try it one more time. Boom, 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 boom. Okay. So they're hitting that wall at a higher frequency, okay, just as if you were to be running towards the wave. And so picture them actually bouncing off of this wall and being received by the this acceptor over here, okay, you would perceive a higher frequency. So basically, when waves like sound or light bounce off of a moving object, if that moving object is the reflector is moving towards you, you're going to perceive a higher frequency of the wave compared to as if it was stationary. And if it was moving away from you, you're going to perceive a lower frequency. Okay. So this is it moving away from you. So a much lower frequency of impact. And again, I would get that. I would have had that bouncing, but I couldn't figure out how to do it. Okay. So the closer the speed is to the speed of the wave, the closer the speed of the observer or the reflector or whatever, the more it's shifted. So I used to have an animation that would illustrate this pretty nicely, but it went bye-bye. So just basically this is the deal. If the ambulance is driving towards you fairly slowly, the frequency is going to be increased by a little bit. But if the ambulance is driving towards you very quickly, the frequency is going to increase by a lot more. Okay, that's pretty much it. Okay, this is the equation that relates the perceived or apparent frequency to the velocity of the object and the velocity of the wave in whatever medium it's in. And this is the original frequency, or the frequency that the source is actually emitting. Okay, so so the apparent frequency is equal to 1 plus or minus. Now, why do you think there's a plus or minus in this equation? Well, that's what is dependent upon if the source is moving away from you or towards you. Okay, how do you know which one to do? Okay, well, if it's moving towards you, you want to use the plus because you want it to increase the frequency. And if it's moving away from you, you want to use the minus because it's going to reduce the frequency. Okay. All right. So sanity check your answer and make sure that they make sense. So what will cause a Doppler effect shift to an observer? If the source is moving, if the observer is moving, or if it bounces off a moving reflector. Okay. So here, let's work a problem with the new equation. So we've got a race car that generates noise with a frequency of 400 hertz, and it's moving to the left with a speed of 50 meters per second. Meanwhile, a car drives to the right at a speed of 10 meters per second. If the speed of sound through air is 330 meters per second, well, what frequency does the car perceive while the race car is moving towards them, right next to them, moving away from them? Okay, so here both the source of the sound is moving at 50 meters per second, and the perceiver of the sound is moving at 10 meters per second. So if the race car is moving towards you, meaning you're both aimed towards each other, and then what's the relative speed between you and the car that's creating the sound? Well, if you're driving to the right at 50, or if he's driving to the right at 50 meters per second, and you're driving to the left at 10 meters per second, the relative speed between you two is going to be 60 meters per second because you're getting closer at a rate of 60 meters each second. Okay, and so if you're moving towards so moving towards, then you're going to use the plus. So 1 plus 50, or I'm sorry, 60 over 330 times 400 gives you whatever that is, 4730, I guess. Or 473 point something. Sorry, yeah, that would make sense. Luckily, I sanity checked my answer. It doesn't make sense that the answer would be 4,000. It's not going to change by that much. Okay. And if the car is moving away from you, um, then you're going to be, when it's right next to you, the speed is going to be 400 hertz. And then as it's moving away from you, your relative speed is still going to be 60, but we're going to use the minus here, okay, because I need the frequency to decrease. So that's 327 hertz. Okay. So this is what happens if you're moving below the speed of sound. This represents the Doppler effect. Okay. Notice that these circles are not concentric, but they do not overlap anywhere. Okay. If you're going slower than the speed of the wave, okay, the waves cannot ever overlap and intersect. Okay. Um, Now, if you're flying at the speed of sound, and this is a jet, so we're flying at the speed of the wave, um, what we get is it's like yelling and then running after it and keeping up with it. Okay, that wave, and meanwhile you're still yelling, so you're sending more waves, and they're adding up and they're adding up. They're constantly overlapping at that point of release. Okay, this is known as a shock wave or a high pressure region. Okay, so let's take a look at. Well, I don't think we can call it a shock wave just yet, but we're close. Um, so this is a picture of a jet that's just breaking the sound barrier, and you can see where this kind of looks like they took a sphere and sliced a section off of it. Okay, what's going on there is that is this section right here where these wave fronts are constantly overlapping and giving you a very constructive interference and constructive interference of a longitudinal wave or a compression wave is the result of it results in a high pressure. Okay, constructive interference in a compression wave results in high pressure. Okay, and that high pressure is causing the water in the air to condense, and you're seeing basically a cloud form where it's breaking the sound barrier. Okay. Now, when something moves faster than the waves themselves, okay, then the waves actually intersect. Okay. Um, and that the result of this overlapping region here, where those waves are intersecting and overlapping, is constructive interference as well. Except rather than having that kind of conical plane shape, this forms in a V shape, or more technically in a cone shape. Um, and so this is actually a shock wave, the result of traveling faster than the speed of a wave, resulting in constructive interference of the waves, and that high pressure region or whatever is a shock wave. So let me pull up the applet for that. It's not gonna. Okay, so this is what that looks like in kind of a 2D view here. What we can see is this is the source of the sound, or the source of the wave. It's breaking the quote unquote sound barrier, and it's leaving its shock wave kind of out in this V-shaped conical region here. Okay, and more of a 3D view, but still not really a 3D view. You can see in this. So here's the waves, or the sound source, wave source traveling. Here it's reflecting back, and so it's there we go. Let me clear the wave. Okay. Um, this is the shock wave that's forming here, and you can see that in this uh, V-shaped region here. And the height of that is higher than the rest of the waves because of that constructive interference. And so anyway, that is that. All right. So back to this. So when you actually get this, you're getting the overlap of spheres of sound, and the overlap of those is going to generate a cone. It's not really a V-shaped phenomena in sound, which is a three-dimensional wave. So here is the jet. It's past this person, but they have not heard the shock wave yet. This person is hearing the shock wave, which in sound that's called a sonic boom. That's what happens when a jet travels faster than the speed of light. They generate a shock wave, and the pressure of that shock wave of that sonic boom can be enough to blow out windows because it is a pressure wave. It is a longitudinal wave. And here we're just hearing the jet noise, whatever, but the sonic boom is actually right there. Anything traveling faster than the speed of sound in air will generate a shock wave, generate a sonic boom. So here's a bullet, and it's being fired out of a high-powered rifle. Um, and there's a couple of interesting things about this. For one, this is the muzzle blast, okay, right here, okay. Um, and here is the shock waves, that V-shaped, cone-shaped shock wave that I told you that would be emitted. But if the bullet is traveling faster than the speed of sound, then that means that you could get hit with the bullet before you even heard the gunshot. Okay, a little spooky. All right. So what happens is if you break the sound barrier, um, and then you keep going faster. Well, this is a shock wave at Mach 3.5. Mach 3.5 means you're traveling at 3.5 times the speed of sound. Okay, and this is a shock wave at Mach 6. Okay, what do you notice different about these shock waves? Okay, meaning the V-shaped lines coming over. Okay, well, the shock wave is more at a sharper angle on here, so that the shock wave gets more tightened to the source of the plane. Okay. Now, if the wave isn't traveling very fast, so here we're talking about the wave of water, okay, then you don't have to travel very fast to create a shock wave. All right. Okay. So, but anyway, since water waves don't travel very fast, you don't have to travel very fast to create a shock wave. This is the shock wave of the duck as it's leaving its shock wave in its path. Okay. Um, Subsonic jets, meaning a jet that's traveling less than Mach 1, less than the speed of sound, will never create a shock wave because the spheres can never overlap. So this what we're seeing is the Doppler effect here, okay, but not a shock wave. Um, and that is it for this. That's it for this unit too. So do the work, and good luck on the test, and we'll go from there.